Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the middle of the 19th century, American astronomy was a field of immense potential and profound provincialism. It existed largely as the domain of gentlemen scholars and civic boosters, a pursuit characterized by descriptive observation and a certain theatrical grandeur. Observatories were erected as monuments to municipal pride. Their telescopes often pointed towards celestial spectacles for public edification. The deep, grinding work of positional astronomy, the rigorous mathematical reduction of data that formed the bedrock of European progress, remained a distant and almost alien discipline. The intellectual firmament over the United States was, in a sense, clear but shallow. It was into this environment that a young, ferociously ambitious Bostonian named Benjamin Apthorp Gould returned, carrying with him an intellectual fire forged in the crucibles of German science. Gould's journey to Europe was a pilgrimage to the very heart of the scientific revolution of his time. He sought out the University of Göttingen, a place where the spirit of Carl Friedrich Gauss permeated every lecture, hall, and laboratory. There, the universe was understood as a system legible through the language of mathematics. Astronomy was a quantitative science, a relentless process of measurement, calculation, and the statistical refinement of error. Under Gauss, Gould absorbed the profound power of the method of least squares, a tool for extracting the most probable truth from a sea of imperfect observations. His subsequent time in Berlin with Johann Franz Encke, director of the Berlin Observatory, provided a complementary education. Encke was a master of systematic astronomy, organizing vast, long-term projects to map the stars and track the movements of planets and comets. He managed his observatory as a research factory, a model of efficiency and focused scientific production. For Gould, this was a revelation. He witnessed a professional ecosystem where science was a career, research was a duty, and rigor was the only accepted currency. Upon his return to the United States in 1848, armed with a Göttingen doctorate, Gould saw his homeland with new eyes. He perceived a scientific landscape lacking a central nervous system, a community without a common standard or a forum for serious, specialized discourse. His solution was an act of audacious intellectual transplantation. In 1849, with his own limited funds and an inexhaustible supply of determination, he founded the Astronomical Journal. This was a radical act. The journal was conceived as a direct American counterpart to the esteemed German publication, the Astronomische Nachrichten. Its purpose was singular: to create a home for mathematical astronomy on American soil and, by its very existence, to compel the field to elevate its standards. The early volumes of the Astronomical Journal stand as a testament to Gould's uncompromising vision. They are slender, dense publications filled with a kind of work that was almost entirely absent from other American scientific venues. One finds page after page of orbital elements for newly discovered asteroids and comets, intricate calculations of planetary perturbations, and theoretical papers on celestial mechanics. The language was overwhelmingly mathematical, featuring complex applications of differential calculus and probability theory. These were papers written for a small, expert audience, designed to be argued over, built upon, and integrated into the global scientific conversation. Gould himself was the journal's editor, primary contributor, and chief fundraiser. He used its pages to publish his own extensive research, but more importantly, he established a benchmark. To be published in the Astronomical Journal was to demonstrate a mastery of the mathematical tools and theoretical frameworks practiced in the great observatories of Europe. This endeavor was far from easy. The journal was a constant financial burden, and its circulation remained small for years. It represented a direct challenge to the more descriptive, accessible style of science popular at the time. Yet, its impact was undeniable. It provided a crucial platform for a new generation of American astronomers who shared Gould's vision. A young Simon Newcomb, who would become the dominant figure in American celestial mechanics, found an outlet for his early, highly technical work in Gould's journal. Asaph Hall, a future discoverer of the moons of Mars, likewise published his precise observational data and calculations within its pages. The journal functioned as a filter and a forge, identifying those committed to the rigorous German model and providing them with a community and a standard to uphold. It slowly but inexorably professionalized the discipline from within. Gould's attempt to institutionalize this vision extended beyond the printed page. His tumultuous tenure as the director of the Dudley Observatory in Albany, New York, was a physical manifestation of the same ideological struggle. The observatory's trustees, a group of prominent local citizens, envisioned a grand public institution, a jewel for their city. Gould, however, saw the opportunity to create America's first true research observatory, a working facility modeled on the Berlin or Pulkovo observatories. He planned for systematic programs of star cataloging and meridian circle observations, the kind of foundational work that wins little public acclaim, but upon which all of astronomy rests. The resulting clash was epic and bitter, a battle between civic pride and scientific purpose. Though Gould ultimately lost the directorship, the conflict itself broadcast his ideals to a national audience, starkly illuminating the chasm between the old, gentlemanly model of science and the new, professional one he championed. The influence of his German mentors is woven through every aspect of this early crusade. The mathematical architecture of the Astronomical Journal, particularly its reliance on statistical data reduction, was a direct inheritance from Gauss. The ideal of the Dudley Observatory as a factory for producing precise, fundamental data was a mirror of Encke's program in Berlin. Gould was more than a student. He was a missionary for scientific methodology. He believed that for America to take its place among the leading scientific nations, it had to adopt the intellectual infrastructure of the leaders. His journal was the first and most critical pillar of that infrastructure. By establishing this beachhead of mathematical rigor, he reshaped the very identity of the American astronomer, transforming the role from a passive observer of celestial beauty into an active, quantitative interrogator of the cosmos. This relentless drive to impose mathematical order upon the vastness of space would soon find a new, unexpected, and profoundly terrestrial focus as the nation itself descended into a conflict that demanded a new kind of calculus, one applied to the very measure of human life. The national cataclysm of the American Civil War presented a problem of an entirely different order. The calculus of celestial mechanics, designed to predict the serene and orderly dance of planets, seemed to whirl away from the chaotic and brutal reality of the battlefield. Yet, for Benjamin Apthorp Gould, the underlying challenge was fundamentally the same. The conflict created a new kind of universe to be measured, a population of over 2 million men whose lives and deaths formed a massive, noisy data set. The Union Army, a force unprecedented in American history, was hemorrhaging lives, with a vast majority of casualties occurring far from any battlefield. Disease, exposure, and inadequate care were the principal agents of death, and the military's understanding of these threats was tragically anecdotal and impressionistic. The war demanded a new kind of accounting, a statistical reckoning with the physical and medical realities of its soldiers. This urgent need for quantitative understanding found its champion in the United States Sanitary Commission, a civilian organization sanctioned by the government. The commission was a pioneering force in public health and logistical support, dedicated to improving the welfare of Union soldiers. Its leaders quickly realized that effective intervention required robust data. They needed to understand the human material they were working with. What was the physical profile of the ideal soldier? How did age, height, or birthplace correlate with resilience or susceptibility to illness? These were questions of actuarial science applied to a military context, and to answer them, the commission turned to the one man in America whose entire career was built upon the science of large-scale measurement and error reduction, Benjamin Gould. Gould's response was to pivot his entire intellectual apparatus from the cosmos to the core. He conceived of the project with the same rigor he had applied to stellar parallax. In his view, each soldier was an observation, a single data point possessing a set of measurable attributes. A population of 1 million soldiers was analogous to 1 million observations of a star, rife with individual variations and potential errors. The goal, as in astronomy, was to process this immense volume of raw information to distill a clear, statistically sound understanding of the whole. He initiated a vast data collection enterprise, creating standardized forms to be filled out at recruitment stations and field hospitals across the Union. These forms captured a soldier's age, height, weight, chest measurement, place of birth, and a host of other physical and demographic details. In this ambitious undertaking, Gould was channeling the intellectual currents flowing from Europe, particularly the work of the Belgian statistician and astronomer Adolphe Quetelet. Quetelet had been a revolutionary figure in the development of what he termed social physics. He proposed that the mathematical laws of probability could be applied to human populations to uncover societal regularities. His concept of el homme moyen, or the average man, was a powerful abstraction. Quetelet argued that by aggregating data from tens of individuals, one could derive a statistical mean representing the central type of a population around which all individual variations were distributed according to a predictable curve. Gould saw in Quetelet's work a direct terrestrial parallel to the methods of his astronomical mentor, Carl Friedrich Gauss. The Gaussian distribution, the familiar bell curve used to describe the distribution of errors in astronomical measurements, was the very same tool Quetelet used to describe the distribution of human heights or weights around the average man. Gould was importing this powerful European framework and deploying it on a scale that dwarfed any of Quetelet's own studies. The culmination of this colossal effort appeared in 1869, a massive volume titled Asterisk Investigations in the Military and Anthropological Statistics of American Soldiers. Asterisk. The book was a landmark, a statistical portrait of the Union Army of breathtaking detail and scope. Within its dense tables and meticulous analyses, Gould laid bare the physical realities of the men who fought the war. He presented detailed statistical breakdowns of recruits by state, comparing the average heights and lung capacities of men from Maine versus men from Ohio. He analyzed the physical characteristics of soldiers of different ancestries, comparing native-born Americans to immigrants from Ireland or Germany. The findings were of immense practical significance. Gould demonstrated with overwhelming statistical evidence that recruits younger than 20 years of age exhibited a dramatically higher rate of mortality from disease. Their physical immaturity made them exceptionally vulnerable to the rigors of camp life. This single discovery provided an empirical foundation for a shift in military recruitment policy, favoring more mature soldiers who were statistically proven to be more resilient. The work also provided a baseline for identifying fitness for duty, allowing medical examiners to move beyond subjective judgment and toward a quantitative assessment of a recruit's physical capacity. Gould's tables function as the first actuarial charts for the American military, allowing for the calculation of risk based on measurable human traits. The influence of this work extended far beyond immediate military application. Gould's asterisk investigations served as a powerful proof of concept for the role of the state in large-scale data gathering and analysis. It became a foundational text for the nascent disciplines of American sociology and physical anthropology, providing a template for how to study a population scientifically. Its most direct intellectual inheritor was Carroll D. Wright, a fellow veteran of the Civil War who would become the first United States Commissioner of Labor. Wright explicitly modeled his own pioneering statistical studies of the American workforce on Gould's methods. He took the principle of applying rigorous statistical inquiry to a population and directed it toward understanding the new industrial economy. Gould, the astronomer, had inadvertently authored one of the seminal documents of American social science, creating a paradigm for data-driven governance that would shape public policy for generations. Having completed this exhaustive survey of the human condition under duress, Gould had brought the discipline of the observatory to the chaos of human conflict. He had measured and catalogued a population of men with the same dispassionate precision he once reserved for the stars, reducing the immense complexity of an army into a series of coherent statistical laws. With the war concluded and this monumental terrestrial catalogue finished, his analytical gaze, having been drawn down to earth by a national crisis, began to lift once more. His ambition returned to the celestial sphere, seeking out a challenge that remained in the heavens, a vast and silent territory that awaited its own systematic measure. The great uncharted void of the southern sky beckoned out. The celestial void south of the equator represented the last great frontier of classical astronomy. While the northern heavens had been subjected to centuries of scrutiny, culminating in the meticulous catalogues of European observatories, the southern sky remained a realm of approximation and incomplete knowledge. Its constellations were known, its brightest jewels admired, but a systematic, rigorous, and comprehensive map was an ambition yet to be realized. For a man like Gould, whose entire career was a testament to the power of systematic measurement, this vast expanse of uncharted data was an irresistible call. It was a challenge perfectly scaled to his formidable energy and his unwavering belief in the primacy of empirical evidence. The opportunity to answer this call came from an unlikely quarter. Domingo Sarmiento, the visionary president of Argentina, was a fervent advocate for education and scientific progress as the engines of national development. He sought to catapult his nation onto the world stage, believing that intellectual capital was as vital as any material resource. To this end, he extended an invitation to Gould in 1869 to establish and direct a new national observatory. The proposition was extraordinary, complete autonomy, and ample funding to build a premier astronomical institution from the ground up, with the explicit mission of charting the southern sky. For Gould, it was the convergence of a lifelong dream with a national ambition. He accepted, leaving behind the established scientific community of the United States for the pampas of South America. The task he faced in Cordoba was monumental. He was creating an institution in a region with almost no existing scientific infrastructure. Every piece of equipment, from the delicate micrometer screws to the massive meridian circle telescope, had to be procured from workshops in Europe and America and transported across thousands of miles of ocean and land. Delays were inevitable. A regional conflict, the Franco-Prussian War, held his primary instruments captive in European ports for months. Yet, Gould was a man for whom idleness was anathema. While awaiting the arrival of his main telescope, he recognized an opportunity to begin a foundational project, one that required the most sensitive and well-calibrated instrument he already possessed to the human eye. His immediate goal was to produce a southern counterpart to the definitive catalogue of the northern sky, the asterisk Uranometria Argentina, published decades earlier by the great German astronomer Friedrich Wilhelm Argelander. Gould viewed Argelander's work as the gold standard for visual stellar photometry, the science of measuring the apparent brightness of stars. He adopted Argelander's systematic approach and magnitude scale as his model, seeking to extend its rigorous methodology to the entire southern celestial hemisphere. The project which he would name the Uranometria Argentina asterisk, aimed to create a complete atlas and catalog of every star visible to the naked eye, down to the 7th magnitude. This was a far more demanding task than it sounds. It required thousands of hours of painstaking observation, conducted night after night, in a methodical sweep of the heavens. Gould and a small team of assistants would lie on their backs in the clear Argentine air, comparing each target star to a set of nearby reference stars whose brightness had been carefully established. They estimated magnitudes through a process of sequential comparison, a technique that demanded immense concentration and consistency. Each star was observed multiple times by different observers on different nights to average out atmospheric variations and personal biases, ensuring the final cataloged magnitude was as precise as humanly possible. This relentless process of observation, comparison, and recording formed the daily rhythm of the new observatory for years. It was a testament to the power of disciplined, repetitive labor in the service of a grand scientific vision. The work was a grind, a form of manual data collection at a cosmic scale, yet it was the essential bedrock upon which all future studies would be built. After nearly a decade of this exhaustive visual survey, the results were published in 1879. The Uranometria Argentina was a landmark achievement. It consisted of a large folio atlas of 14 star charts, beautifully engraved to show the constellations of the southern sky with unprecedented accuracy. Accompanying the atlas was a volume containing the definitive catalog, listing the positions and meticulously determined magnitudes for 7,156 stars. For the first time, astronomers worldwide had a reliable, systematic, and comprehensive reference for the southern celestial sphere. The work immediately became the foundational text for Southern Hemisphere astronomy, the standard against which all other observations were measured. The impact was profound and immediate. The Argentine National Observatory, an institution that a decade earlier was merely an idea in the minds of a president and an astronomer, was now recognized as the world's leading center for the study of the southern sky. Gould had single-handedly shifted the global center of gravity for an entire branch of astronomical research. The data he produced was invaluable, providing the raw material for studies of stellar distribution and galactic structure. His successor at Cordoba, John M. Tone, would directly build upon this foundation, using the Uranometria Argentina as the starting point for even deeper surveys. Gould had provided the master map of the visible terrain. His next endeavor would be to plumb its depths, to extend the survey far beyond the limits of human vision and into the dense star fields of the Milky Way. This first great catalog, born of patience and the keenness of the human eye, was the necessary reconnaissance for the far grander campaign that was to follow. The completion of the Uranometria Argentina was a monumental achievement, a comprehensive atlas of the southern sky visible to the unaided eye. It established the Argentine National Observatory as a premier astronomical institution. Yet, for Benjamin Apthorp Gould, this meticulous cartography of the obvious was merely the prelude. The true scientific frontier lay deeper in the vast, uncounted stellar populations that formed the very fabric of the Milky Way. The first great catalog was the necessary reconnaissance for the far grander campaign that was to follow, a campaign to extend the census of the heavens to the faintest reachable stars. He sought to create a southern counterpart to the definitive stellar map of the northern hemisphere, Friedrich Argelinder's celebrated Cordoba Durchmusterung. This new project would consume the remainder of Gould's time in Argentina and would become his most enduring scientific monument. The endeavor, which would come to be known as the Cordoba Durchmusterung, represented a challenge of an entirely different order of magnitude. A Durchmusterung, a German term meaning a thorough survey or running through, was an exhaustive cataloging of every star down to a specific faintness in a given region of the sky. Argelinder had set the standard. Gould intended to complete the global picture. This required a systematic, almost industrial process of observation, night after grueling night, for more than a decade. The instrument of choice was the meridian circle, a telescope constrained to pivot only along the north to south line bisecting the sky. As the Earth rotated, strips of the heavens would drift through the telescope's field of view. An observer, peering into the eyepiece, would call out the precise moment a star crossed a set of fine wires, while simultaneously estimating its brightness or magnitude. An assistant sitting nearby would meticulously record these two vital coordinates, right ascension and declination, along with the estimated magnitude for thousands upon thousands of stars. This was a task of heroic monotony. One can imagine the scene repeating endlessly in the quiet of a high Argentine plain, the dim red light of land, the steady ticking of the observatory clock, the observer's low voice announcing a star's transit, and the scratch of the assistant's pen in the logbook. The process demanded immense discipline and consistency. Visual magnitude estimates are inherently subjective, yet Gould and his small, dedicated team, including his successor, John Tome, developed a rigorous internal standard that gave their data, remarkable reliability. Over the course of 12 years, they accumulated observations for what would ultimately become 6.13 and 9.50, three individual stars. While this colossal visual survey formed the core of the project, Gould also demonstrated his forward thinking by pioneering the use of astrophotography to map dense southern star clusters. These photographic plates, among the very first of their kind in the southern hemisphere, were a testament to his embrace of new technology, even as the main catalog relied on the proven, albeit Herculean, visual method to achieve its comprehensive scope. From this immense sea of data, a discovery of profound structural significance emerged. As Gould and his team analyzed the distribution of the brightest, most luminous stars in their catalog, they uncovered a startling anomaly. They found that these brilliant, predominantly young stars were arranged in a great band that was tilted at an angle of approximately 20 degrees relative to the main plane of the Milky Way. This was an unexpected and fundamental feature of our local galactic neighborhood. It was as if, within the grand, flat disk of our galaxy, there existed a secondary, tilted ring of stellar nurseries. This structure, a vast, flattened association of stars and gas clouds spanning thousands of light years, and including many familiar constellations like Orion and Scorpius, became known as the Gould Belt. Its discovery was the first strong evidence that the galaxy's structure, on a local scale, was far more complex than a simple, monolithic disk. The scientific value of the Cordoba Durchmusterung extended far beyond this singular discovery. Its true power lay in its utility as a foundational dataset for the emerging field of statistical astronomy, the attempt to deduce the galaxy's large-scale structure from star counts. The catalog found its most immediate and influential application in the hands of the Dutch astronomer Jacobus Kapteyn. At the turn of the 20th century, Kapteyn was embarking on his own ambitious project to model the entire stellar system. His work required a complete and uniform stellar census of both the northern and southern skies. Argelinder's Bonner Durchmusterung provided the northern data. Gould's Cordoba Durchmusterung provided the indispensable southern foundation. By combining these two monumental catalogs, Kapteyn was able to perform the first truly global statistical analysis of stellar distribution. His painstaking work culminated in the famous Kapteyn universe model of 1922. This model depicted the galaxy as a relatively small, flattened, lens-shaped island of stars, with our sun positioned very close to its center, while later discoveries would reveal this picture to be incomplete, primarily due to the obscuring effects of interstellar dust, which Kapteyn had underestimated. His model was the most sophisticated and empirically grounded picture of the Milky Way of its time. It represented the pinnacle of what could be achieved through classical star counting. The entire edifice of the Kapteyn universe rested upon two great pillars of data, and the southern pillar was the Cordoba Durchmusterung. Without Gould's years of relentless effort in Argentina, Kapteyn's view of the cosmos would have been hemispherical, his conclusions speculative. The publication of the full catalog stretched from 1892 to 1932, a testament to its sheer volume and the meticulous care taken in its reduction and printing. Continuing long after Gould had departed Argentina, and even after his death, it became the fundamental reference for southern celestial mechanics and astrophysics for half a century. The Gould Belt itself remains a subject of intense study in modern astrophysics, a nearby laboratory for understanding the dynamics of star formation, with its origin still debated, perhaps the result of a massive supernova explosion or the impact of a high-velocity gas cloud on the galactic disk. Having completed the celestial census from his remote outpost, Gould had provided the essential raw material for the first generation of galactic architects. His focus, upon his eventual return to the United States, would shift from the grand scale of the cosmos to the precise measure of the Earth itself, applying his astronomical discipline to connect continents and synchronize a rapidly modernizing world. Upon returning to the United States in 1885, a figure seasoned by 2 decades of relentless work under the southern stars, Benjamin Gould directed his formidable energies toward a problem of terrestrial, global significance. The world was shrinking, bound together by the undersea cables and continental railways that were the triumphs of the age. This new interconnectedness demanded a new level of precision. While celestial charts could guide ships across oceans, the synchronization of commerce, science, and governance required a definitive, shared understanding of the Earth's own grid. The accurate determination of longitude, a puzzle that had vexed mariners for centuries, now presented a critical challenge for modernizing civilization. Existing methods, reliant on lunar distances or the transport of chronometers, were fraught with cumulative errors and logistical hurdles, yielding results inadequate for the geodetic and temporal precision the era required. Gould saw the solution in the very technology that created the demand, the electric telegraph. The concept of using telegraphic signals to compare local times between observatories was established, championed in America by the U.S. Coast Survey. Gould's contribution, however, was to elevate this technique into a tool of supreme international accuracy. He became a principal advocate and a master practitioner of the method, refining its execution to an art form. The procedure was elegant in its logic. An astronomer at one observatory would tap a telegraph key in perfect rhythm with the swings of a master pendulum clock. Miles away, a second astronomer would record the exact arrival time of these electronic pulses against their own local clock. The process was then reversed by exchanging signals in both directions. The finite travel time of the electrical pulse along the wire could be precisely calculated and eliminated from the equation. What remained was the pure, unadulterated difference in local sidereal time between the two locations, a direct and exquisitely accurate measure of their difference in longitude. His crowning achievement in this domain was the organization and execution of the transatlantic longitude campaigns. These endeavors were monumental logistical and scientific undertakings aimed at establishing an unbreakable geodetic link between the North American and European continents. The project connected the United States Naval Observatory in Washington with the Royal Observatory at Greenwich, the world's prime meridian. This was far more than an academic exercise. By fixing the longitude of American observatories relative to Greenwich with unprecedented certainty, Gould's work provided the fundamental reference point for the entire cartographic enterprise of the United States. Every map, every property line, and every railroad schedule on the continent ultimately depended on this foundational measurement. He transformed a continental scientific community into a fully integrated node within a global system. His meticulous work with telegraph keys and transit circles effectively anchoring America to the rest of the world. This final great project serves as a powerful lens through which to view the entirety of Benjamin Gould's career. His life's work presents a compelling duality. He was, on one hand, a tireless producer of monumental data sets, a celestial accountant of the highest order. The Uranometria Argentina gave the southern sky its definitive visual atlas, while the Cordoba Durchmusterung and its associated zone catalogs provided the raw positional data that would fuel galactic astronomy for generations. These were foundational contributions, immense blocks of empirical knowledge hewn from a previously uncharted wilderness. They enabled astronomers like Jacobus, Kapteyn, and Hilo Shapley to begin sketching the true scale and structure of the Milky Way. Gould provided the exhaustive, reliable inventory of the local cosmos from which grander theories could be built. Simultaneously, and perhaps more profoundly, his legacy is that of a scientific architect. His most enduring impact arose from his construction of the intellectual and institutional infrastructure that allowed American science to mature. While his contemporaries pursued singular discoveries, Gould dedicated himself to the often thankless, yet essential, task of building the systems that make discovery possible. The Astronomical Journal was his first and most lasting blueprint, a vessel for rigorous, peer-vetted communication that imposed a standard of excellence on a field previously characterized by scattered and informal correspondence. It cultivated a national community of professional astronomers where one had existed in name only. His work with the United States Sanitary Commission during the Civil War revealed the same architectural impulse applied to a national crisis. He organized a sprawling data collection enterprise to build an actuarial and statistical foundation for understanding the health and mortality of soldiers, transforming anecdotal evidence into systematic knowledge. In Argentina, he did more than map the sky. He built a national observatory from the ground up, training a generation of local astronomers and establishing a permanent scientific institution in a nation that had none. His insistence on rigorous methods, his battles for funding, and his unwavering commitment to the publication of results set a powerful precedent for how state-sponsored science could and should operate. Thus, the full measure of his career transcends the sum of his publications. Benjamin Apthorp Gould was the indispensable organizer, the standard setter, the institutional founder. He understood that great science requires more than brilliant minds. It requires a stable, interconnected, and self-critical community. It requires reliable journals, professionally managed observatories, and shared standards of data reduction and analysis. He dedicated his life to creating these very things. He labored for decades on catalogs that were, by their very nature, obsolete upon the arrival of the photographic plate, yet the professionalizing rigor he instilled in their creation was timeless. His career demonstrates a fundamental truth about scientific progress, that it depends as much on the meticulous, disciplined architect as it does on the visionary theorist. He may have appeared to future generations as a man obsessed with the fine details of stellar positions and terrestrial coordinates, yet it was through this very obsession that he constructed the framework upon which American astronomy built its ascent to world leadership. His legacy is written across the sky in the catalogs that bear his name, and it is embedded in the very foundations of the scientific institutions he fought so tirelessly to create.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.